Problem 1. Easy sum. Let's start with the number n. For example, let's select n is equal to 6 and create a set A from 6 to 1 and then choose a denominator m. For example, let's select m is equal to 4 and divide each element of A by m and find the remainder r and store the reminders in a new set B and finally add the elements of B.
This is problem number 2, pairwise sum and divide. Step 1, pairwise sum. This means adding adjacent element in the array. For example, the array has 1, 2, 3, 4. Add sum of pairs like this. Pair 1 equals 1 plus 2 equals 3 and pair 2 equals 3 plus 4 equals 7. Then step 2, sum of pairs. Sum of pairs equals 3 plus 7 equals 10. Then step 3, divide by array size. Finally, you divide the total sum of pairs by the number of elements in the array. In this case, the array has 4 elements. We can divide 10 by 4 equals 2.5. If you were allowed to use floating point in division, or we can divide 10 by 4 equals 2 if you need to use integer division. So with the array has 1, 2, 3, 4, you end up with results of 2 if you're using integer division.
Problem 3, power calculation. We need to calculate a sum of s equal to k to the power of n series, where k and n are integers. The challenge is to find the last 2 digits of s to several test cases. Each test case provides values of k and n. For example, is one of test case k equal to 3 and n equal 4. We calculate 1 to the power of 4, 2 to the power of 4 and 3 to the power of 4, which are 1, 16 and 81 respectively. Add them together equal to 98. The last 2 digits of the sum are 98. The process repeat for all test cases. By focusing only on the last 2 digits, we simplify calculation for large values of k and n. The key is efficiently handling large sums using modular arithmetic to extract last 2 digits to keep the problem manageable even when the numbers are very large.
Problem 4, Scalar Product. Given a sequence of numbers defined as follows, a0 equal to naught, a1 equal to c, and we can see ai plus 2. This sequence generates 2D vectors from v1 to vn. Let S be the best set of scalar product of vi and vj. Let's find the numbers of distinct residuals modulo m in S. For example, if we take c equal to 4, m equal to 5, and n equal to 3. And then the sequence becomes as we can see. The vectors are v1 equal to 4, 3, v2 equal to 2, 3, v3 is 2, 4. According to the above steps, we can get these scalar products in modulo 5. There are 2 distinct residuals modulo 5 in S. They are 3 and 4. Therefore, we can get the result as 2.
Problem 5. Summing the k n series. First, input values to n. Then check the value of n should be greater than or equal to 1 and less than or equal to 0. After that, input values to k. Then check the given constraint, that is greater than or equal to 0 and the less than or equal to 103. After that, create 2 variables name, which is t initially equal to 0 and x which is initially equal to 1. After that, following these steps. First, find the value of x to the power k and add 1 to the value of x. After that, find the value of t by adding the now value of t and the value of x to the power k. After that, check if the x is lower than n. Then display the value of t. If we get k as 3 and n as 5, you will get t as 386 after following these steps.
Problem number 6. Fun with series. In the problem number 6, we start with the series Gn given that the formula for the sequence pattern where a and b are integers. This means each term in the series depends on the previous 2 terms scaled by a and b. In the step 2, we analyze our questions, which we have 2 types. Type 1, we should compare S1p and S2p for different p values. Here we count how many times S1p is greater than S2p and how many times S2P is greater than S1P, and how many times they are equal. In the second question, they are asked to calculate the S modulo 10 to the power 9 plus 7. So in the step 3, we calculate the S1 for the value 1, where we put the value 1, and S2 using the specific coefficient, and find where S1 will be equal to 1, S2 1 will be equal to 2. Next, in the step 4, we calculate for p equal to and update our coefficient same as above. So there we get S12 equal to and S22 equal to 4. As we proceed to the next step, we count the scenarios. We discover that there are no instances where S1P exceeds S2P. Two scenarios where S2P is greater and again no equalities. Finally, in the step 6, we do the second part of our question by evaluating p equal 1 with our established coefficient and calculate the final results with S modulo 10 to the power 9 plus 7, which will be equal to the 1.
Problem 7. Circle summation. Circle summation is a method to sum numbers arranged in a circular structure. Imagine n children sitting in a circle and each holding a number. Then, starting at a random child, in each round, the current child adds the sum of their clockwise and anti-clockwise neighbors' numbers to his own value. Then, the next child clockwise takes his turn. This will be done m times. For example, with 4, 8, 3, 6, 5. Suppose it's starting at value 8 and this will be done 2 rounds. In round 1, 8 becomes 8 plus 4 plus 3 equal 15. In round 2, 3 becomes 3 plus 4, 15 plus 6 equal 24. So the final values are 4, 15, 24, 6 and 5.
Problem 8. Counting equation. Let's break down this problem by step. Imagine we have two whole numbers. Let's call them x and y. Now let's say we want to find all possible ways to add these two numbers together to get the third number z. Step 1. Generate all possible pairs. We start by listing all possible combinations of x and y. For example, if both numbers can be 0 and 1 or 2, we have pairs like 0, 0, 0, 1, 0, 2 and so on. Step 2. Calculate values of z. For each pair, we simply add two numbers to get z. So for 0 and 1, z would be 1. Step 3. Identify unique values of z. Now we want to count only the different values of z. We don't want to count the same value multiple times. For instance, if we get z equals 3 from two different pairs, we count only once. Step 4. Count the unique values of z. Finally, we count the total number of unique values of z we found. This number represents the total number of distinct equations of forms of x plus y equal z. By following these steps, we can systematically solve the problems and find the exact number of unique equations for a given range of x and y values.
XOR. XOR is a logic operation where the result is 1 or true if two binary inputs are different. Here the list A of numbers from 1 to n. For example, if n equals 3, then A is 1, 2 and 3. If n equals 4, then A is 1, 2 and 3 and 4. For each query, you are given a number, a k and a range p and r. Then we have to find all pairs I and j in that range where j is greater than I. For example, if A is 1, 2 and 3 and k equals 2 and p and r equals 2 and 3. Pair 1 and 2, here I equals 1 and j equals 2. A1 XOR operation, A2, the result is 3. Then k XOR operation 3, the result is 1.
Same problem. Rational sum. The series given as sigma n equal 1 to infinity 1 over n into n plus 1. The trick here is decomposition. Each term can be broken into two simple fractions using partial fractions as 1 over n into n plus 1 equal 1 over n minus 1 over n plus 1. Now if we expand the series using decomposition, it looks like this. Here the key idea is telescopic. Most of the term cancelling out everything except the very first term and the last negative term. So after cancellation, we left with 1 minus 1 over n plus 1. Finally, n approaches infinity. The term 1 over n plus 1 approaches 0. That leaves with 1.
Problem 11, girlfriend and necklaces. So the problem is ask you to find the number of necklaces that has equal or more than number of red beads than blue beads. The first line of the input should be contain an integer d, the number of test cases, and each line after the test cases there should be the number of beats in the necklaces. And so the process of finding the number of necklaces is the equation here in as follows. This equation where the limit of k plus 1 over 2 and the upper limit of k. So if you input the value of k even number, then you should find that if the number is even number by k modulus 2 equal or not equal to 0. If that is an even number, then the process of finding the equation is here as below, where the upper limit is k over 2, the lower limit is k over 2 and upper limit is k. If the provided number is odd number, then the lower limit should be k plus 1 over 2 and the upper limit should be k. By inputting these numbers, you can find the number of necklaces.